friends, in this video we are going to discuss synchronous rotors. Let's see how the salient pole rotor. See, I am drawing the salient pole rotor. For example, I am taking for 4 pole. I am taking for 4 pole. The diagram is like this. This is my salient pole type rotor. And see how the cylindrical type of rotor. Cylindrical type of my rotor is like this. Exactly, this is the cylindrical type of my rotor. See, actually, for example, this is North Pole, South Pole, North Pole and South Pole. Here, this is North Pole and this is South Pole. And how the winding here? The winding is here like this. This is the winding in salient pole type. This winding is called field winding. The field winding excited by DC supply. And here the rotor outer periphery slotted for winding. We know that. And these are the windings of my cylindrical machine. And the rotor is like this. And the rotor is like this. This is my cylindrical type rotor and this is my salient pole type rotor. And can you tell me, this is the D axis or Q axis? First give me the answer. Yeah, very good answer. This is the axis which flows through the pole centers. That's why this is a direct axis. Exactly. And if the axis flows through 90 degrees to the in quadrature to the D axis, quadrature bole to 90 degrees. So in quadrature to the D axis is nothing but the Q axis. This is my Q axis and this is my D axis. This is the cylindrical type of my rotor. Now you have a test. Let's tell me, this is the Q axis or D axis? Yeah, exactly. This is a D axis because the axis which flows through the pole center is 100% correct answer. Now tell me, this is the D axis or Q axis? Sir, Q axis? Sir, D axis? Which is correct answer? Which is correct answer? Yeah, give me the answer. No. This is not a Q axis. This is also D axis. Sir, how? Sir, when this is a Q axis, then this also should be Q axis. Is I said you like that? Am I said you like that? No. What I said you, the axis which is flows through the pole centers. These are my 2 poles. The axis which flows through the pole centers is exactly polar axis or direct axis. Okay, sir, this is also D axis and this is also D axis. Okay, no problem. Now show me where is my Q axis. Where is my Q axis? There is no Q axis. Yeah, very good answer. Very good answer. This is my Q axis. This is correct? What I said you, the angle between D axis and Q axis is 90 degrees. Can you tell me what is the angle here? This is 90 degrees? No, actually this completely 90 degrees, nothing but this is 45 degrees and this is 45 degrees. Here the angle between q-axis and d-axis is only 45 degrees, but I said you the angle between d-axis and q-axis is 90 degrees. Which is correct answer? Is this is correct answer or this is correct answer? Tell me. Both are correct answers. Sir, how sir? Here only we have 45 degrees, but you said that this is a d-axis, this is a q-axis. For that, we have an explanation, no problem. Generally, we know the formula, theta electrical is equals to P by 2 times of theta mechanical. P by 2 times of theta mechanical. Are you okay? Theta electrical is equals to theta mechanical. This is the mechanical angle 45 degrees multiplied with number of poles. Number of poles are 4 and 2. 2 ones are 2 twos are 45 twos are 90 degrees. Theta electrical is equals to 90 degrees. So now tell me, is this is the 45 degrees or 90 degrees? This is 45 degrees in terms of mechanical, but when comes to electrical angle, this is a 90 degrees. Now tell me, the angle between q-axis and d-axis is, the angle between q-axis and d-axis is option A, 90 degrees electrical, option B, 90 degrees mechanical. Which is correct answer? Exactly. 90 degrees electrical is the correct answer. 90 degrees electrical is the correct answer. 90 degrees mechanical is 100% wrong answer. Right? So this is generally the main difference in terms of axis. Right. Next one. Here we can derive another formula. Actually we derived in induction machine also. We can written as in terms of omega. Omega electrical is equals to omega mechanical and P by 2. Omega electrical is 2 pi f and omega mechanical is 2 pi n out of 60 and P by 2. 2 pi gets cancelled. So n is equals to 120 f by p. This is called as synchronous speed. You know this. This is called as synchronous speed. Yes or no? Right? So we derived this already and well-known formula for all you people. Yes or no? Right. So let's go for subject. Now let's differentiate between these two. Yeah. First see, what is the meaning of salient pole? What is the meaning? Tell me. Here, salient pole, nothing but poles are projecting outside. Poles are projecting outside. That is the meaning, is a salient pole. See here, poles are projecting outside. This is called salient pole or projecting poles. But here the thing is very different. Here, out of total rotor periphery, 1/3 portion is used for pole formation. 1/3 of the rotor used for poles formation, and remaining 2/3 of the poles is used for slots and windings. This is the cylindrical type of rotor. See here, actually in total 1/3, nothing but 120 degrees. 120 degrees is used for poles. 120 degrees used for poles. Remaining 240 degrees for slots and winding. Nothing but 60 degrees and 60 degrees for poles and 120 degrees and 120 degrees for winding. This is for two-pole machine. For example, if I constructed for a four-pole machine, then even though whatever the number of poles, the poles portion is 120 degrees and the slot portion is 240 degrees. 120 degrees nothing but 30, 30, 30, 30. This is the 430s. And remaining winding portion is 460s, 4 6 are 240, 4 3s are 12. This is the way of winding in cylindrical type machine, but in sail and pole machine, here poles are projecting outside. On that pole periphery, we are placing the field winding. We are placing the field winding. This is the first point. And next, generally here we are using concentrated winding. This is a concentrated winding. See, the winding is similar to transformer. In transformer also we are placing the winding like this. So in transformer and in sail and pole machine we are using concentrated winding. But here we are using distributed winding. This is a distributed winding, but this is a concentrated winding. Remember this one, very important. And next one. See carefully. See here, generally the number of poles in this machine, the number of poles are minimum 6 and maximum 120. Minimum number of poles 6. Sir, you draw here only 4 poles just for understanding purpose. Okay, but generally the minimum number of poles are 6 and maximum 120. But in generally we are using around 10 to 20 poles in our regular applications. So here more number of poles we can use. But here the possibility of poles is only either 2 or 4. That's it. There is no possibility of other than this. We have only either 2 poles or 4 poles. This is a cylindrical type rotor. I said you synchronous machine nothing but synchronous speed. Synchronous speed nothing but 120 F by P. For example, my frequency 50 hertz. If the number of poles are 10, 0, 0 gets cancelled, then the synchronous speed is, when 0, 0 cancel, 12 paisa, 600 RPM. If it is 20 poles, again 0, 0 cancel, then you get 300 RPM. The speed of sail and pole machine, the speed range of sail and pole machine is 300 to 600 RPM. Whereas in cylindrical machine, for 4 poles, the speed is, for 4 poles, the speed is 1500 RPM, and for 2 poles, the speed is 3000 RPM, 1500 and 3000 RPM. So here the speed range is 300 to 600, but here the speed range is 1500 to 3000 RPM. Are you okay? So this is. Now tell me, which generator used for low speed applications? Can you tell me? For low speed applications, which generator is preferable? The sail and pole type is used for low speed applications, whereas cylindrical generator is used for high speed applications. They will ask you question, for low speed application, which type of winding is preferable? For low speed applications, the concentrated winding is preferable. As usually we saw in transformer also. In transformer, the speed is 0, concentrated winding. Whereas for high speed applications, distributed winding is preferable. Low speed applications, concentrated winding, and high speed applications, distributed winding. This is another thing. And tell me, generally, in between these two, which machine having more diameter? They will ask you a question like that. Large diameter, nothing but which machine? Or in sail and pole machine, the diameter is large or small? See here, when number of poles increases, the diameter increases. So the salient type is a large diameter. Here diameter is large, but axial length is small. Here length is small, but diameter is more. Whereas in our cylindrical machine, we have only 2 or 4 poles. For 2 or 4 poles, the diameter is less. Here, small diameter. But see here, the axial length is large. The large axial length and small diameter. This is also very, 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 very important. They will ask you a question like this. For example, 10 meters length, 10 meters length, 2 meters diameter. What they given? 10 meters length, 2 meters diameter. Is this is a sail and pole type or cylindrical type? See here, more length, less diameter. So this is a cylindrical type of rotor. Like that you have to mention the answer. Are you getting or not? Right now tell me, here axial length is more, but how much more? Here diameter is more, how much more than length? Here the diameter is 5 to 7 times of the axial length. Here the diameter is 5 to 7 times of the axial length. Whereas here the axial length is 5 to 7 times of the diameter. Axial length is 5 to 7 times of the diameter. If the diameter is large, then the speed minimum. More diameter, nothing but low speed. Less diameter, nothing but high speed. Less diameter, nothing but high speed. Like that, they will ask you a question. Finally, sail and pole alternators used at where we are using the sail and pole alternators. Tell me. The sail and pole alternators are used for low speed applications. Example, hydro power plants. In hydro power plants, we are using sail and pole type of alternator. They will ask you a question, which of the following is used in hydro power station? So sail and pole type is used in hydro power plants. Now this cylindrical type machine used in nuclear power plants and thermal power plants. Nuclear power plants and thermal power plants, because the steam speed is very high. This is a very, very important concept. Finally, they will ask you a question. Which of the following is called turbo alternator? Tell me. This cylindrical type of generator is called turbo alternator. This is a turbo alternator. Then what about this? This is a hydro alternator. This is a hydro alternator and this is a turbo alternator. Are you getting or not? Getting or not? This is very important. Okay, just we saw the only one difference is that on diameter or speed that and winding. And next difference. Let's see. What about stability? What about stability? Tell me which generator is more stable? Motor or generator? Which machine is more stable? I said you the stability is directly proportional to air gap. So here see, here air gap length is more, here less, here more, here less. But here always less. Yes or no? So tell me here, sail and pole type more stable or less stable? This is a more stable machine. And the cylindrical type is a less stable comparatively. Less stable and more stable. This is another. And next and last concept. Difference between them. Let's see here. First of all, and see here the air gap length along the D axis and the air gap length along the Q axis. Tell me air gap between D axis and Q axis, where the air gap length is maximum, where the air gap length is minimum. The air gap length is minimum along the D axis. And towards the Q axis, air gap length increases, and at the Q axis, the air gap length is maximum. Air gap length is minimum along the D axis and increases towards the Q axis, and at Q axis, air gap length is maximum. But here, along the D axis and Q axis, air gap length is same. Air gap length is same along the D axis and Q axis. Nothing but, listen here. Nothing but the air gap length along the Q axis is greater than air gap length along the D axis. But here, air gap length along the Q axis is exactly equals to air gap length along the D axis. Here, non-uniform air gap length. But here, uniform air gap length. Here, non-uniform flux distribution. But here, uniform flux distribution. When the flux distribution is uniform, then EMF is sinusoidal. What is that? When the flux distribution is uniform, EMF is sinusoidal. Here EMF is sinusoidal. When the flux distribution is non-uniform, here EMF is not a sinusoidal. EMF is not a sinusoidal. Here EMF not a sinusoidal, but here EMF is a sinusoidal. This is about EMF. Here stability is more, but EMF not sinusoidal. Here stability is less, but EMF is sinusoidal. Then here stability is the good symptom, but EMF is the bad symptom because it is a non-sinusoidal. Then how we can get the sinusoidal EMF in silent pole machine? Tell me how we can get a sinusoidal EMF. We have a small trick. What is the trick? Here we have a poles, right? These poles are changed like this. How? These poles we have to change like this. We have to change like this. This process is called chamfering. This process is called chamfering. What it is called? It is called chamfering. By chamfering the salient poles, we can get an sinusoidal EMF. This is a small change in salient pole type. They will ask you a question, chamfering is preferred or required in induction machine, DC machine, silent pole synchronous machine, cylindrical pole synchronous machine. Then the answer is in silent pole machine. By chamfering the poles, we can get sinusoidal EMF, but here no need of chamfering because EMF is already a sinusoidal wave. These are the difference between silent pole and cylindrical type. Synchronous machines are synchronous rotors. Very, very, very important thing. Understood? Thank you.